All right, guys. So obviously in the first video, we left off where we were just starting to look at the graphs of inverse functions and noticed that they were symmetrical about the line y equals x. With one exception, we noticed that there was this particular case where f of x was equal to the square root of x minus 3, g of x was equal to x squared plus 3, and they weren't quite symmetrical. And the reason for that, we said, was there was kind of two problems. The first, when we're looking at the graphs, and here those are once again, was that our second function, the x square root of x minus 3, would also need to have a negative square root of x minus 3 in order to look symmetrical. Now, that's fine, and now they do look okay, but the problem is that our second one is not a function any longer. It does not pass the vertical line test. And so that's why we can't have this negative square root of x minus 3 as well. But that means that our first function, we're going to have to change a little bit. Notice that it's not a one-to-one function. It does not pass the horizontal line test. And so what we have to do is what's called restricting the domain, which is different from a domain restriction. I know that that is a confusing concept and that they are very similar in name to each other. But a domain restriction and a restricted domain are in fact separate ideas. The idea of a restricted domain is instead of looking at the entire function x squared plus 3, we're only going to look at part of it. And we're only going to look at half of it, really, is what we're going to do. And so to pick that half on a graph, you can kind of just decide using the graph what that's going to be. In fact, the correct one is going to be to say where x is greater than or equal to 0. If you try to say less than or equal to 0, graphically you're going to see that they are not the same. They're not going to be symmetrical. And so using a graph is one way. We're going to also look at some of the algebraic ways to know what the restricted domain should be. So let's take a look at that now. First of all, what is the restricted domain? Well, the definition of that is that we're going to limit the x values or the inputs for a function which is not one-to-one, so that the inverse is a function. And so let's do that for kind of both directions. Let's start by looking at it for a quadratic, and then we will look at it going the other direction for a square root or a radical function. So that's kind of where the inverses fit in with the radicals. Okay, so let's go ahead and start with this basic example. We've got f of x is equal to x squared, where x is greater than or equal to 0. So let's just go step by step through those steps of finding an inverse. So step number 1, remember, is that we replace f of x with y and write this as y equals x squared. Step number 2, we're going to solve for x. And so to do that, we're going to take the square root of both sides of our equation. Now, because on the right side, the square root of x squared is still taking the square root of a variable, that means that we do right now need to put a plus and minus sign in front of y, or rather the square root of y. So for right now, x is equal to a positive or negative square root of y. Now is when we're going to swap x and y, so plus and minus the square root of x is equal to y. And remember, for the last step, we're going to replace y with f inverse of x and set that equal to the rest of our equation. However, we're not going to be able to say plus and minus the square root of x. If you think about what that would look like, that would be your square root function, but also its reflection, and that's not going to pass the vertical line test. And so what we need to now decide is, are we going to keep the positive or are we going to use the negative? To be able to tell, we're going to look at the domain, the restricted domain, which is x is greater than or equal to 0. Because it says x is greater than or equal to 0, that's going to tell us to choose the positive rather than the negative in front of the square root of x. So because it's positive, we actually don't need to write anything in front. We can just write the square root of x. Had it been x is less than or equal to 0, we would have picked the negative, and then that would have been a negative sign in front of the square root of x. And so there it is. Here's our final answer. In fact, if you were to graph both of these, in fact, let's just do it real quick. So if we were to graph x squared, where x is greater than or equal to 0, along with the positive square root of x, notice that they are, in fact, inverses of one another, and they do, in fact, are symmetric about that line y equals x. Now, had we said negative square root of x, which would not have been correct because it says x is greater than or equal to 0, then right, now it's not going to match. The only way we would have said negative square root of x would have been to have said x is less than or equal to 0, in which case notice that that does in fact create a graph where the inverses are symmetrical about that line y equals x. All right, let's take a look at a couple more examples of quadratics. So for the next example, we've got f of x equals x squared minus 2, again, where x is greater than or equal to 0. So step number 1, replace f of x with y. And now let's solve for x. So we'll add 2 to both sides. So y plus 2 is equal to x squared. And now to get x by itself, take the square root of both sides of your equation. Again, this is where that solving radicals that we did and solving quadratics that we've done are all going to kind of help us out. And at this point, remember, when you take the square root of x squared, that's just x, but you've got to make sure to include the plus and minus sign in front of your square root of y plus 2. At this point, x is by itself, so we are ready to swap x and y. So positive and negative square root of x plus 2 is equal to y. And now we're ready for that final step. So kind of two parts to that final step. The first is we're going to replace y with f inverse of x. The second is we're going to decide whether to keep the plus or the minus sign in front of our square root. Since it's x is greater than or equal to 0, we're going to choose to keep the plus sign or the positive. And that means that we won't need to actually put anything in front of our radical. We can just copy down the square root of x plus 2. And here's our final answer. Once again, if you want to check, just go to Desmos or wherever you'd like to graph. Type in the first equation, which was x squared minus 2. Make sure that you, in the squiggled brackets, type x greater than or equal to 0. And for your second equation, remember we picked the positive, and it was the square root of x plus 2. And once you've done that, you should notice that your graph is now symmetrical about y equals x. And so yes, we do in fact have the inverse for our function. All right, so let's take a look at one last example for quadratics, and then we'll look at what that means for both cubics as well as radical functions. So this last example, we've got f of x is equal to x plus 1 squared minus 4, with x being less than or equal to negative 1. Now, first of all, why is it x is less than or equal to negative 1 rather than x is less than or equal to 0? Well, let's take a look at our graph of x plus 1 squared minus 4 first. So again, that was parentheses x plus 1 squared minus 4. And so here is that graph. If we try to just say where x is less than or equal to 0, the problem is going to be that you don't get half of your graph. And that's because, and I guess I should have this as plus 1, and that's because the vertex is not on an x value of 0. In fact, if you think about what the vertex would have been, the vertex would have been at negative 1 and negative 4. And so you have to base your restricted domain on the vertex of your parabola, because that's where the axis of symmetry is. That's where you can cut your function into half. And so that's why we're saying that x has to be less than or equal to negative 1, as opposed to x is less than or equal to 0, because if we try to just say 0, notice that we get too much of our graph. When we have that as the correct value at negative 1, we do in fact get half of our graph, which is what we want when we're trying to find the inverse. Okay, so long story short, that's why we need for our x value to be different than 0 for this particular problem. However, the steps to finding the inverse are still the same. So replace f of x with y, and now let's solve for x. So we'll do that by first adding 4 to both sides. So we've got y plus 4 is equal to the quantity x plus 1 squared. To get rid of our exponent of 2, let's go ahead and take the square root of both sides. When we do so, the right side will just be x plus 1. The left side, for right now, will be plus and minus the square root of y plus 4. So to get x by itself, one last step to go, which is to subtract 1 from both sides. Make sure that when you do that, that the 1 goes after the radical, not inside. So a minus 1 outside, and that'll leave us with x is equal to a positive or negative square root of y plus 4 minus 1. At this point, we are ready to now swap x and y. So we now have that plus and minus the square root of x plus 4 rather, minus 1 is equal to y. And now we're ready to write this as our inverse function. So we'll replace y with f inverse of x is equal to, we now need to decide whether to keep the plus or the minus. And notice that our sign is different this time. It's a less than or equal to sign rather than greater than or equal to. That less than or equal to is going to be what tells us to use the negative in front of our square root. So we had not had to do that just yet. This was the first time we've had to use the negative in front of our radical instead of a positive. So we do need to make sure we include that. And here's our inverse function. So let's go ahead and use Desmos to check one last time. So that would be a negative square root of x plus 4, and then minus 1 outside. And in fact, when you look at the graph, they are symmetrical about that line y equals x. Okay, so that about does it for quadratic. We have two more types of functions we are going to look at in this video, which is we're going to look at cubic as well as radical. So for our cubic, we're going to just go ahead and look at these. Now here's the nice part about cubic functions is that cubic functions, at least the ones that we're going to look at, are all one-to-one. What that means is that you don't have to have a restricted domain. So the nice part about cubic functions is you don't have to worry about a restricted domain the same way that you do with quadratic and with radicals. So that's kind of nice. That's the nice part about having functions that are one-to-one. In fact, that's why when you think about it, go back to where we were solving for the inverse originally, where we were looking at linear functions. Notice that all of these linear functions were also one-to-one. And in fact, all linear functions are one-to-one. And that's why, again, for all of these problems, we had no restricted domain. So kind of going back and looking at why we hadn't had to worry about that before, if a function's one-to-one, you don't have to worry about a restricted domain. Only when it is not one-to-one do you have to worry about that. So really for cubic, we're just going to go through our steps to finding the inverse, and that should be pretty much it. So again, step 1, replace f of x with y. Step number 2, solve for x. We'll do that by subtracting 1 and now dividing by 2. So it looks like y minus 1 over 2 is equal to x cubed. Now we will take not the square root, but the cube root of both sides of our equation. Because it's a cube root, you don't have to worry about plus and minus. It's just the cube root of y minus 1 over 2. And now we're ready to swap x and y. So that's the cube root of x minus 1 over 2 is equal to y. And last step, step 4, replace y with f inverse of x. The rest of it you leave the same. And there's our inverse function. Now for this particular example, I will go ahead and graph it to show you what that looks like. For the remaining two, we will probably skip the graphing part, and I'll just leave it up to you to check on your own. So 2x cubed plus 1 was our first equation. Again, I will go ahead and type that in here. So 2x cubed, and then plus 1. So then our inverse function, in order to get your cube root sign, you'll need to hit functions and then find that nth root and type in the cube root. And that's going to be x minus 1 all over 2. And here are your two functions. So again, and feel free to zoom in or out however you'd like to, but notice that those are in fact symmetrical about that line y equals x. Okay, so that'll be probably the only one we graph for cubic, but let's go ahead and do a couple more examples of cubic just to make sure it makes sense. Go through those step by step. So step number one, obviously replace f of x with y. Step number two, we're going to solve for x, which is really kind of the longest step if you think about it. So add over the 2, divide by 3, and you'll get that y plus 2 over 3 is equal to x cubed. So once again, to get x by itself, we're going to take cube root of both sides of our equation. And that's going to, again, not need a plus and minus sign, but the cube root sign obviously needs to be there. But the cube root of y plus 2 over 3 is going to be equal to x, at which point we are ready to swap our variables. So that's the cube root of x plus 2 over 3 is equal to y. And now final step, replace y with f inverse of x and copy down the rest of your expression, which is the cube root of x plus 2 over 3. And here's your final answer. Okay, so let's do one last example of cubic, and then we can talk about radicals and how we'll use those and how to write a restricted domain for your inverse function of those. But our last example of cubics first, we've got f of x equals 1/2 parentheses x minus 3 cubed plus 6. So again, step number one, let's replace f of x with y. And now we can go ahead and start solving for x. So let's subtract 6 from both sides. So y minus 6 is equal to 1/2 x minus 3 cubed. Now let's get rid of the 1/2 by multiplying by the reciprocal of 1/2, which is 2 over 1, or just 2, on both sides of the equation. If you want to distribute on the left side, you can, but you don't necessarily have to. And now we're ready to take cube root of both sides. So we'll take cube root of both sides of our equation. Again, you don't need a plus and minus when you're working with cube roots, only with roots that are even, so square roots, fourth roots, and so on. We really won't look at any fourth roots, sixth roots, and so on. So really just square roots are the only problems where you'd have to worry about that. Now we're not quite done solving for x. There is still one last step to go, which if you can see what that is, we're going to have to add by 3 on both sides of our equation. And that should give us x by itself is equal to the cube root of 2y minus 12 underneath the radical plus 3 outside. We're now ready to go ahead and swap our variables around. So that would be 2x minus 12 underneath the radical now is equal to y. And now we are ready to rewrite y as the inverse function and call it f inverse of x is equal to, and then just copy down the rest of that equation. So the cube root of 2x minus 12 plus 3. And at that point, we are done. Okay, so obviously cube roots are quite a bit easier just because, again, you don't really have to worry about the restricted domain stuff that we had to worry about for quadratics as well as for radicals. So just kind of keep that in mind, that they are a little bit easier than the other two. Okay, so let's talk about radicals. Let's talk about how those are going to be a little bit more difficult when we consider our restricted domains. So when we've got a radical, let's go ahead and start by solving for the inverse the same way we would any other type of equation. So we're going to start by replacing f of x with y. So y is equal to 2 radical x minus 3. So now let's go ahead and solve for x. So we'll start by dividing both sides by 2. So we'll have y over 2 is equal to the square root of x minus 3. And now we're ready to go ahead and square both sides of our equation. So again, here's where solving radicals becomes kind of useful. So now we've got y over 2 squared is equal to x minus 3. And then from there, we'll add over the 3. So we'll have y over 2 squared plus 3 is equal to x. At this point, we're ready to swap x and y. So we'll have that x over 2 squared plus 3 is equal to y. And now we're ready to write it as the inverse function. So we will replace y with f inverse of x, and then copy down the rest of the equation, which is the x over 2 squared plus 3. Now, at this point, if you tried to graph both of these, you're going to end up with a graph where, again, they're not going to match. And that's because for our inverse function, it's got too much stuff. We need to kind of cut our inverse function in half. And so what's useful is to think about what is the vertex of this equation right here. Well, the vertex is the point 0, 3. It is in vertex form, so take the opposite of what's inside. There isn't any numbers being added or subtracted. That's why it's going to be 0. And then the plus 3 outside gives you the 3. So now let's think about how to write our restricted domain. We're going to have x and a number. That number needs to be the same as our x value of the vertex. And then let's go back and look at our number in front of the radical. That number 2 was a positive number. So a positive number implies that we need it to be a greater than or equal to sign. So that means that we need to say that this is going to be where x is greater than or equal to 0. And now we've got our inverse function. In fact, let's go ahead and check our graph and see if that does in fact work. So our original function was 2 multiplied by radical x, I believe minus 3. Let's double check. Yeah, minus 3 underneath the radical. So here is our original function. For our inverse function, we have said that that is going to be in parentheses x over 2. And then close your parentheses, squared plus 3. Now, once again, we said we can't have that entire function. We said the vertex was at 0, 3. And we only want the part that's going to match, which we said since 2 is a positive number, it's going to have to be where x is greater than or equal to the x value of your vertex, which is where x is greater than or equal to 0. And in fact, we have an inverse that matches. Okay, so let's do a couple more examples of this just to make sure it all makes sense, and that should be it for this video. So in the second one, f of x is equal to negative 3 radical x plus 4. Again, let's start the same way. Let's start by replacing f of x with y. And then we'll go ahead and solve for x. So divide both sides by negative 3. So that'll be y over negative 3 is equal to the square root of x plus 4. Now we'll raise both sides to the same power as our index, so we'll raise both sides to the power of 2. So now we've got that y over negative 3 squared is equal to x plus 4. So now let's go ahead and subtract over the 4. So y over negative 3 squared is minus 4 is equal to x. And now we're ready to swap our variables. So we will say that x over negative 3 squared minus 4 is equal to y. And now we're ready to rewrite y as our inverse function, f inverse of x. Now again, we're going to just copy down our equation in its entirety, x over negative 3 squared minus 4. But now we need to decide what our restricted domain is going to be. So starting with identifying what the vertex is of our new quadratic. Again, there's nothing inside the parentheses being added or subtracted from x, so the x value is still 0. The y value is going to be negative 4. And so again, for our domain restriction, we're going to have to use x and the x value for our vertex, which is 0. This time it was a negative 3 in front of our radical. Negative implies we're going to use less than or equal to as our inequality sign. So that would be a restriction of x being less than or equal to 0. And here's our final answer. All right. Now, obviously, you can also have cube roots. The nice part about cube roots is that you don't necessarily need to worry about a restricted domain the same way that for cubic functions, we did not have to worry about that as well. So that'll be kind of nice because we'll be able to just solve this one like normal. And so let's go ahead and do that now real quick, just so we can look at cube roots as well. So step number one, replace f of x with y. And then we'll go ahead and start solving for x. So we'll start actually by cubing both sides of our equation. That way your cube root and your cube are going to go ahead and cancel one another out. So we'll have that y cubed is equal to negative x plus 4. Next, we can go ahead and subtract 4 from both sides. So that'll be y cubed minus 4 is equal to negative x. And then to get x by itself, either multiply or divide both sides by negative 1. Really, that's just going to change your signs all the way throughout your equation to get that negative y cubed plus 4 is equal to x. Now we can go ahead and swap our variables. So negative x cubed plus 4 is equal to y. And then final step, replace y with f inverse of x. And then copy down the rest of your equation. Now again, x to the third power, we've already talked about cubic functions, are 1 to 1. So there is no need for a restricted domain in this case. Again, restricted domains only something that you have to worry about for quadratic and for radical functions. All right, guys, that is it for this video. That is it for 7.4. In the next section, 7.5, we're going to talk about what's called function composition, and in particular, how we can use it to verify that an inverse of a function is in fact the inverse. So a way, besides looking at the graph, that you can tell that the inverse is truly the inverse of a function. Until then, have a good rest of your day.